All right, so you're all welcome once again to this session for Physics 1. Basically, we'll be looking at higher order partial derivatives. I'll just take you through some examples to basically understand one or two things and other things. It will continue another day, another time. And I would also like to say I'm always available. So if you need anything, you can send a message and we can always arrange. If it's one-to-one, we can always arrange and have a tutorial session. I kindly urge all of you to make use of the chats, or if you have a question, kindly raise your hand and I will unmute you for you to ask your question. You are currently muted because we want to reduce the interactions we have. So because of time, I won't waste much time, but to start. So you realize that this semester's course, actually, you have to do a revision of your differentiation because you need that a lot. So if you are still lacking behind in differentiation, I'm kindly urging you that you actually go through your differentiation one more time because the whole course is actually all about differentiation and integration. So in our last semester course, you realize we did those two topics, differentiation and integration. We did talk about what a function was as well. And we're looking at basic examples of function, such that if I have f of x, you realize that it is what? Just a function of one variable. But if I write f of x, y, you realize that this is a function of two variables. So in our last semester course, when we're just looking at a function of one variable, you realize that if you had f of x to be equal to y, with our derivative, we're looking at dy over dx. But this time, with your function of two variables or more variables, you realize that you have what? X and you have y as well. So because you have x and y, it means you are looking at two derivatives in one. That is where your partial derivatives comes in. So the symbol for that is this, partial. So that if I have the function f of x, y to be a function of two variables, then we are saying that I can express this as the partial derivative of the function f with respect to x and the partial derivative of the function f with respect to y. This is what we are calling words, partial words derivative. So you take the partial of the two variables. So I have the partial derivative of x, of f with respect to x, and the partial derivative of f with respect to what? Y. Then, so this is just the first step. So you realize that this is our first derivative. So our first derivative. Or you have your first order. First order. Okay. But with this derivative, we can look at the higher form of it. That is the highest order, the higher order we are looking at. So when we talk about order, we are looking at the highest derivative you have. So you realize that the highest derivative for this is just 1. So you differentiate it once, means the order is 1. If you differentiate twice, it means you have order 2. So what we are saying is that with this same function, if I have f of x, y, this is just order 1, and this is order 2. You can find the highest order of dates. So I could differentiate this function f with respect to x, then differentiate this again. So I have 2, 2. What this means is that the derivative, so derivative of f taken twice with respect to x. That is what it means. It means that I differentiate my function for the first time, f of x, f with respect to x. Then I differentiate the second time again. So you realize that this becomes the second order. If I want a third order, then I can have the partial derivative of f with respect to x cubed. So what it means that you differentiate, you take the derivative of f with respect to x 3 times. With respect to x 3 times. Let's use a basic example to do that. So let's say I have an example, f of x, y to be equal to 3x squared plus 2. And you are asked to find the partial derivative of x for the second order. So I want to find partial derivative of f second order with respect to x. So what it means is that 1, we first take the partial derivative of f with respect to x. And this is going to be that. So let's differentiate this with respect to x. If I differentiate this with respect to x, what do I get? This gives me 6x because you multiply this times that minus 1 here. So I have 6x. Then the second order, which is f x squared, implies that you differentiate this again with respect to what x. So you are differentiating the function f twice or 2 times. This is a constant, so it goes to 0. That is why you have this. So if I differentiate this again, what do I have? 6. So this implies that the partial derivative, the second order, with respect to x, it's equal to 6. If you have questions, you can still raise your hand for questions, or you can type in as well in the chat. Okay, so let's take another example. I have my function f of x, y to be equal to x to the power 4 y squared minus x squared y to the power 6. Let's take some. So the first thing I want to do is find the partial derivative of f with respect to x, but I'm taking what? The second or the first. Okay, let's do for the first. So for the first order, we are differentiating our function with respect to what? X. So we are doing all for x. So we take this part. So any other thing is a constant. If we are differentiating with respect to x, it means any other variable is a constant. So y is a constant. So this is multiplying that. So since this is multiplication, you realize that y squared is a constant. So I'm differentiating with respect to x. So if I differentiate with respect to x here, I have 4 times what? X cubed. Y is a constant multiplying, so that doesn't become what? A constant. If y was on its own, then we'd say it's what? A constant. Minus, you differentiate this as well, x, and this gives us 2x y to the power 6. So what do I have? I have 4x cubed y squared minus 2x y to the power 6. So you realize this is our first order. And we are still talking about highest what? Order. So highest order, let's say we have order 2. So I have this to the power f x squared. So when you have order 2, what do? The first thing we do is first you find f, the partial derivative of f with respect to x. Then you differentiate your results as well for your second order. So the second order here, we are going to differentiate this function. So we are still differentiating with respect to x. So if we do find a derivative, this is going to give us what? 12x squared y squared. Y is still a constant, which is multiplying, minus, if you find a derivative of x here, it is 1. So I have 2y to the power 6. We can still go on to another highest order, which is the third one with respect to x, so that the partial derivative of f of order 3 means that you first do for the first order, second order, and the third order. So to do that, you realize that I have what? Differentiates with respect to x. So 2 multiplies this, you have what? 24x y squared minus this. This is a constant. Don't forget, this is a constant. There is no component of x here. So if I'm differentiating a constant, that goes to what? 0. Look at the difference. This is not the same as this. You realize that this had what? The x with it. So you could differentiate, and it is multiplication. So y then is considered what? As a constant. This is considered as a constant. But you realize that for this part, it is what? Just 2y alone. So that if I'm doing the partial derivative with respect to 1, then the others are considered what? Constant. That is why this goes to 0. So that this becomes what? My final what? Result. If I had to, let's say, I had to find, this is still our function, and you're asked to find the derivative, let's say, squared of f, y, partial derivative of x. What does this mean? This means that we are to find the derivative with respect to what? X, then with respect to y as well. So you can take the derivative with respect to x, then with respect to y as well. So you have 2, you have this, and I have that as well. So I have, so let's solve for this example. So we know the partial derivative of f with respect to y. So I can find my partial derivative of f with respect to y. That gives me what? So this. So I have 2x to the power 4y minus this part, which is 6x squared y to the power 5. So that if I want to find, so this is for the first part. For this, then with respect to x, it is order 2. So with respect to x, what do I have? It means I'm differentiating this with respect to x, which is going to give me 8x cubed this is still a constant. Y is a constant. Y is multiplying. So I have y, then minus 12x y to the power 5. That is what we have here. Okay. So basically, these are the higher orders we are talking about. In other books, you realize that instead of writing the partial derivative, let's say writing partial derivative of f with respect to x, you realize that you have f subscript x. It means the same thing. If I have partial derivative, if I have f subscript y, it means I have partial derivative of f with respect to y. If you have f x x, it means I have second order. So you differentiate twice with respect to what? X. And f y implies that I differentiate twice with respect to y as well. So basically, this is what the highest order is all about. This is what the highest order is all about. Let's take another example. But before then, if you have any questions, you can kindly raise your hands. Okay, so if you don't have any question, I would continue. So let's take another example as we go through again. I have the function f of x. So this is a function of 3 variables. And this is equal to z cubed y squared ln x. And you are asked to find, we want to find f x, x, y, z, z. Okay. Okay, so someone is asking, why to the third order? Okay, so to the third order, this is cube. It is not squared, it is cube. So that was a mistake. So this is cube, not squared. Thank you so much for the correction. So this is what we want to do. You have the function and you want to differentiate, find a partial derivative. If you realize you first have to differentiate with respect to x, differentiate again with respect to x, y, z, z again. So we are going to use this example to look at that. So I first have my partial derivative with respect to x. So this I said is partial derivative of f with respect to x. So we are differentiating this function with respect to x. So you realize that from here, all these are constants. That is multiplying our x. But the x is what? Ln x. If you differentiate ln x, what do you have? You have 1 over x. So it means I have z cubed y squared divided by x. This is equally z cubed y squared x to the power minus 1 if you bring it up. Then the next one is f x x. That is the second one. So this time I'm differentiating this again with respect to what? X. So differentiating with respect to x, don't forget this comes, the power multiplies the whole function. So I have -1 here. Then I have z cubed y squared, then -1. And this will give us x to the power -2. Okay, x to the power -2, which is same as having negative z cubed y squared divided by x squared. That is the second order. Then the third order says what? You have f x x y. This time we are differentiating our function with respect to what? Y. We are differentiating with respect to y. So if I differentiate with respect to y, what do I have? I have 2. So I have -2 z cubed y divided by x squared. That is for this part. Then the next order is differentiating with respect to z. So I'm differentiating this with respect to z. And in doing that, with respect to z, so I have f, x, x, y, z. So we differentiate this with respect to z. And what do I have? I have 3 here. So 3 multiplies 2 to give us 6. So -6 z squared y divided by x squared. Then the last term, which is this. So for my last term, I have f, x, x, y, z, z. It means that the next result, the results you had, differentiates with respect to z. So I'm differentiating this with respect to z. So I have what? This times that, which is -12 z y divided by x squared. So you realize that it's all about what? Differentiation, in which you have to get it right. So I'll pause here. If you have questions, kindly raise your hands for your questions. Okay, else we continue. Okay, so you realize that so far we have looked at what? Our partial what? Derivatives and highest orders. So now the next thing to look at is total differentials. If we say total differentials, what do we mean by that? So I still have a function f of x. Let's say f of x, y, and z to be equal to s cubed. Okay, so before then, we have total differentials. Total differentials. So we start from just a simple example. If I have a function f of x, y to be equal to 3x squared y, and you are asked to find the differential of the total differential for this function. Don't forget, because it's a function of what? Two variables, we first need to find the partial derivatives. Partial derivatives of each variable. So here I'm looking at the partial derivative of f with respect to x and the partial derivative of f with respect to y. Okay, so if I'm able to find the partial derivatives, it means that then the next thing, my total derivative or the total differential. So total differential is going to be this, my partial derivative of f with respect to x times dx, plus my partial derivative of f with respect to y times the y. This is the total derivative. This. So that if I have, so we'll do this example. So that if I have a function, let's say I have f with respect to u, v, and w, it means that my total differential, let's say t, or what you call it, is going to be the partial derivative of f with respect to u times du plus the partial derivative of f with respect to v times dv plus the partial derivative of f with respect to w times dw. That is what it means. So then with this example, let's look at it. Our partial derivative of f with respect to x is going to be, this is squared. So I have 6xy. Then the partial derivative of f with respect to y, if you differentiate this with respect to y, you have 3x squared. This implies that my total derivative, our total differential or derivative, differential is going to be what? 6xy dx plus 3x squared dy. This is what the total words differential you are looking at. Let's take another example. I have my function f with respect to x, y, z, and this is equal to x cubed yz plus xy plus z plus 3. And I want to find the total differential updates. So what it first means is that I need to find the partial derivative of f with respect to x, the partial derivative of f with respect to y, then the partial derivative of f with respect to z. So let's find this with respect to x. So in doing this with respect to x, what do I have? I have 3x squared y z plus, this gives me what? Y. This is a constant, so it will go to 0. This is also a constant, so that goes to 0 because we are differentiating with respect to x. Then with respect to y, what do I have here? I have, if I differentiate this part with respect to y, I have x cubed z plus, this side is what? X. This goes to 0. Then with respect to z, I have what? X cubed here, y, x cubed y, plus, there's no variable here for z, so it goes to 0 plus what? 1 for this part, and this goes towards 0. So that's my total differential. Let's say the total differential, which is df, the total differential df is going to be the partial derivative of f with respect to x times dx plus partial derivative of f with respect to y dy plus partial derivative of f with respect to z dz. So my total differential df is going to be equal to this. So I have this times dx, then this times dy. So I have 3 here, 3 x squared y z plus y dx plus this, which is x cubed z plus x dy plus x cubed y plus 1 dz. So this becomes what? The total derivative I have. If I had given this function to you at a certain point, let's say I gave it to you at a certain point at 1, 2, 3, it means that after this becomes x, y, and z. So that you substitute wherever you see x, it's 1, y is 2, and z is what? 3. So if you do this substitution here, you realize that if I do that at a certain point, then this gives me 20 dx plus 4 dy plus 3 dx. Basically, this is what our partial partial differentiation, higher orders, and total differentials as well. Okay. Any question for now? If we are okay and we are getting it, you can send it into the chat to let me know that you are following. If you are following, let me know you are following in the chat room. Okay. So then, all right, great. Thank you for following. So let's continue. Thank you for following. Then the next thing we are looking at is we have the composites and implicit functions. But before then, let's look at this. The chain rule. I mean, in last semester, we saw the chain rule. So let's have the chain rule. The chain rule. This is to help us understand the composites we are talking about. So let's say I give you this same function I had previously. This function f of x, y, z, which was equal to x cubed yz plus xy plus z plus 3. And I give you x. I tell you x, it's equal to 3 cos t. Then y is also equal to 3 sine t. Then z is equal to 2t. What do you see? You realize that our initial function is a function of what? X, y, and z. That is what you have here. But if I take x, x is also a function of what? T. Y is a function of what? T. And z is also what? A function of what? T. So it means that f as well is a function of t. That is what it means here. That f is also a function of t. So my f is also a function of what? T. But this is what we initially had. So that if I ask you to find the derivative, the f, the t, because they are all functions of t, it means that f is also a function of t. So I can find the derivative of this function with respect to what? T. And how do I do that? Because the initial function I have, it's already in this form. Are we going to substitute this? So it means that we have this cube. So you have to find the cube of this and multiply by this, multiply by that to solve. Is that how we go up? Are we going to go about? You can go that way, but it can be a little complicated as well. So one of the ways to look at it's using what? The chain rule. Because our function is a function of another function as well. So the chain rule is the best we can use. So we can first find the function. So what you do is, let me use a different ink. I find the partial derivative of the function. So I find the partial derivative of f with respect to x. Then I take the function x again and find the derivative with respect to what? T. So dx dt. So you first take the partial derivative of your function with respect to x. But what is x? X is equal to this. So I need to find the derivative of x with respect to t. So this is t. This is t. Plus, would have taken the partial derivative of f with respect to y, but our y is a function of t as well. So times dy dt plus the partial derivative of f with respect to z. Then z is also a function of t. So I take the derivative of z with respect to what? T. And this is what you call the chain rule. So this is our chain rule because our function is a function of another function. If you remember when we were doing the composite function, you realize that for our composite function, when we had f, but f is also what? A function of this. So this was the composite we were looking at. So this is something like that. So if you know this, then we can solve. So we already know the partial derivatives for this individual functions that we already solved here. So I need to find the derivative of this ones, this. So let's take the derivative, the x dt. The x dt, if I differentiate cos t, what do I get? If we differentiate cos, we get what? Sine or negative sine. So we get negative sine. So it means I have negative 3 sine t. Then the y dt is going to, if you differentiate sine, you get cos. So I have 3 cos t. Then the z dt is going to be equal to what? 2. So we multiply this by that and this by that. So what I have is, so now my df dt, df dt is going to be the partial derivative of this with respect to x. That was 3x squared yz minus y times this, which is minus sine t, plus this was x cubed z plus x times 3 cos t, plus the third part, the z part was x cubed y plus 1 times 2. So this is what we have. So this is what we are using here. We had this, so you multiply by that. So this is how the chain rule, it's like the chain rule. Okay, so you need more practice. The good thing is that you have to do a lot of practice on your own to get the understanding, because the more you practice, the more you understand what you are doing. Okay, so then understanding this, we can then look at the composite function, or what we call the chain rule. So basically, this is what we have done. Then if you remember as well, so the composite function is still the chain rule we are looking at when we had a function. So I had a function, let me write this, a function f of x, it's equal to x squared plus 1 all to the power 17. Then I have gx to be equal to x squared plus 1. If I want to find, let's take another function, h of t, it's equal to t to the power 17. You remember when we're doing composite function, you can write f of x gx, means that I substitute this for that. I hope we still remember composite functions. So you can substitute this for this. It means that wherever I see x, I'm going to substitute for this. That is what it means. Okay. So if I have h g of x, what does it mean? It means that wherever I see this is, I substitute for what? G of what? X. and this is my g of what? X. So that if I substitute that, wherever I see t, I substitute for this, implies that I have t, and I'm substituting for g of x. So I have x squared plus 1 to the power 17. Don't forget x squared plus 1 to the power 17, it's equal to this as well. So this is the composite function we're looking at. So that if f of x, it's equal to this. From here, f of x, it's equal to this, h g of x. Then it means that my derivative, f prime of x, is going to be equal to the derivative h of what? H prime. Then you have g of x times the derivative of g of x as well. We may not understand unless we take an example. So the best thing to do is take an example. So what I mean from here is that if y is a function, of u, then we would have written uy. That is what it means. And this same u is a function. It's a function of x. Then dy dx for the second part. So if I want to find dy dx, is going to be equal to the derivative of y with respect to u times du dx. That is what it means. So let me take this example. The best thing is always use an example. So I have, let's say I have y to be equal to x squared plus 1 to the power 17. Then u, it's equal to x squared plus 1. It means that what it means here is that you realize that y is equal to u to the power 17. That is what it means here, because this is u. This is u. So it means that this is what I have. So that if I want to find dy dx, it means I have dy du, which is this, times du dx, which is also that. So that if I do that, dy du gives me 17 to the power u to the power 16 times du dx is 2. So this is going to be 2x. I have 2x here, 17. So 17 times 2, it's actually going to give me 34. So I could have 34x. And you know what u is? We know u is x squared plus 1 to the power 17. All we are doing is, if I have, so let's say I give you a function f of x. So from here, okay, so from here, I ask you to differentiate the function with respect to x. So you are differentiating dy dx. You realize that for this function, it's not going to be easy to differentiate. Why? Because of the power. The power is too big to do that. You have this of this. I mean, 17 of that. So what we are saying is, you first differentiate the whole of this. Let me use a different marker. I differentiate this so that if I differentiate, you are treating it as 1. I have 17 x squared plus 1 to the power 16 times, you differentiate what is in the brackets. Basically, that is all that we are doing. I differentiate what is in the bracket as well with respect to x. And if I differentiate that, I have what? 2x. So basically, it's still the same thing I have done here. I have y to be equal to s to the power 5 plus 3x to the power 16. And you are asked to differentiate dy dx. You realize that looking at this, then it's going to be what's difficult. That is where you are looking at your chain rule and your composite function. So it says, if I have something like this, the first thing to do is first differentiate the whole of this function. So I treat this function, x to the power 5 plus 3x, as just one variable. So if I do that, it means I have what? 16 x to the power 5 plus 3x minus 1. You know when you are doing your differentiation. So I have 15 times, then differentiate what is in the bracket as well. So I differentiate what is in the bracket with respect to x. And that gives me 5x to the power 4 plus 3. So that is then your result. So you realize that, so all the steps we're going through was just to help us understand how we are arriving at this. Okay, so another example. So I'm taking my time here. Another example is having y to be equal to 3x squared minus 5 cubed. I want to find dy dx. It says what? Differentiate this, the whole of this with respect to x. So we differentiate this whole thing and treat this. So the whole idea is we are treating this as what? A variable. So it's just like saying that from here, u is equal to 3x squared minus 5. Just like, I mean, I want to say that. So I treat this whole thing as 1, so that I have 3x squared minus 5, 2. Because if you differentiate, that is what you have, times what you have in the brackets. So what do I have in the brackets? I have 3x squared minus 5. And 3x squared minus 5, you differentiate with respect to x. And that gives me 6x squared. So what do I have? I have 18x squared minus 5 to the power 2. This then becomes what? My final words answer. Should I take another example? Another example is, I have, all right, so okay, so you can ask your question, Evans. Unmute yourself.
Yes, please, ma'am. I'll unmute myself.
Okay.
Please,
okay.
for the just solved question, the question that we just solved. The one in brackets, yes, please.
This.
Yes, please.
Okay.
Is that the one that we differentiated? Is that the one after the dot?
Okay, yes. So this is the function. This is the whole function. So we are treating this whole function as u. At u to be equal to 3x squared minus 5.
Okay.
So what it means is that I have u. So if this is so, it means that I have y to be equal to u to the power 3.
Yes, please.
So then I'm differentiating the y du. And the y du is going to give me what? 3u squared. That is this. I know u is this. So 3, sorry, I left the 3 here. Yeah, so I left the 3 here. Okay. So u, it's equal to this.
Yes, please.
Yeah, I think so. It was a 3 I left out.
And I mean, we had 6x squared, but I think it will be 6x.
Hey, 6x. Yeah, thank you. 6x. Okay, 6x. Thank you so much. Yeah, so I have that. So you differentiate this and you have 6x. Please, any more question?
No, please, madam. That's all.
You can kindly mute yourself. Okay, thank you. Let's take another example. So please, like, you realize I'm making small mistakes. I'm making mistakes. You should realize that you also need to take your time as well to get it done. So you make sure you don't rush into it. X squared plus 2x plus 1 to the power 12. So this will be our last example. I don't want us to spend so much time as well, so that, I mean, the next time we can continue the y, the x. What do we have? We differentiate the whole of this. So we want to treat this, let's say if it's a variable u, it means you have y to be equal to u to the power 12. So that if I find the y, the u, I have 12 u to the power 11. So from here, you realize I have 12 u. What is u? U is this, x squared plus 2x plus 1 to the power 11 times, you differentiate what you have in the bracket. If I differentiate, I have 2x plus 2. This is what? A constant, so it goes to 0. So this, then it's your result. So before we go off, let me just write a few examples you could try on your own. A few examples you could try on your own, take a screenshot and send to me, and I'll look at it for you. Like I said, I'm always available. You just have to arrange. Let's discuss and arrange a time. If you just want one-on-one tutorial, 2 minus z to the power 4. Okay, 3 have z to be equal to x plus 1 over x to the power 3 over 7. So you try your hands on this. Few examples to look at and see. Okay, so before we go off, let me just introduce the implicit differentiation. implicit differentiation. If you remember, when we started looking at function, we made mention of explicit and implicit. So in our implicit, we made mention that you can't actually tell which is a function of which. So implicit differentiation. So when you had a function and we couldn't tell which one is a function of the other. Example is if I have x squared plus y squared to be equal to 1. We can't actually tell which is a function of which. If we could tell, that was our explicit. But with this, is x a function of y or y a function of x? Then we have an implicit towards function. So if we have this function, we know this is an equation. What is the equation of this? Which figure, geometric figure, has this equation? Which geometric figure? Which geometric figure has this equation? Evans, if your hand is up, you can unmute yourself. Yes, this is equation of what?
Equation of circle.
Yeah. Okay, very good. So Alexander says this is an equation of what? A circle. Very good. So we know this is an equation of what? A circle. This is our r squared. So our r is 1 here. So I want to find the differentiation for this. So I want to differentiate. So you want to imagine that y is a function of x and obeys this implicit equation. So what we do is, if I want to do this with respect to x. So I have x squared plus 1, y squared to be equal to 1. This is what I want to do. So I want to differentiate with respect to x. It says that the first thing you do, 1, is you differentiate both sides of the equation with respect to x. Differentiates both sides with respect to x. So what it means is, all right, I'll do that. So this implies that I have this, the x of x squared plus y squared to be equal to d over dx 1. This I can write as, so I'm differentiating each of the variables or each of the terms with respect to x. Dx, x squared here, plus dx, y squared, plus d to be equal to, so this is equal to dx 1. So that is our first term. I will kindly scroll for you to look at the questions. So this is the first term you do. This is the first term. After this first term, let's continue solving. So if I solve here, this is a function with respect to x. So I still have what? If I differentiate this, I have 2x plus, this is a function. This function is a function of y, but we are differentiating with respect to x. So we differentiate the function y here to have 2y. Then we multiply by we still have dy dx. for that. This is a constant. So if I differentiate a constant, it's equal to what? 0. So let's look at that side again. You differentiate all the terms with respect to what? X. So I differentiate this with respect to X, this with respect to X, this with respect to X. This is already a function of X. So if I differentiate with respect to X, I have this. This, you realize you are differentiating with respect to X, but it's a function of Y. So you differentiate your term with respect to the function there, which is Y. So that I have 2y times dy dx to be equal to 0. Then the next step, 2, you group all dy dx on one side. So that if I do that, you realize that I have, so from here, what do I have? I have 2x. Let me take this to the other side. Minus 2y dy dx. But what do I want to find? This is what I'm looking for, dy dx. So what can I do? I can divide both sides by you can divide both sides by this. So that if I divide both sides by that, what do I have? I have, let's say I have 2y. Let me write 2y dy dx to be equal to 2x here. I mean, whichever way, or negative 2x, so that dy, okay, let me move from here, get more space. So that dy dx is going to be the differential of this. Divide by both sides. If you divide by both sides, what do you have? I have minus 2y minus 2x, oh, okay, 2x x divided by my 2y. This is what I have. So let me go back again. So the first thing says what? Differentiate both sides with respect to x. So all that we do is we take for each term, we differentiate each of the terms with respect to x. So this with respect to x, this with respect to x, then this with respect to x as well. When you finish, the results you get, the next thing is you group all dy dx to one side, then you group all the other terms at the other side as well. What we want to achieve is what? To make dy dx the subject so that we could solve for that. So this is where we are ending today. The next time we meet again, we'll start from the implicit differentiation. I don't want us to do so much. I mean, we also want to conserve data as well. So this is the example. You can write it. Then what I'm going to do now is I'm going to unmute all of you. If you have anything to say, you can say before we go off. So now I have given you the power to unmute yourself and talk if you want to.
Okay.
Okay, so if you don't have anything else, we'll kindly Zoom.
Recording in progress.
Okay, bye-bye, madam.
Bye.
Happy birthday to Panda.